Hello class, welcome to day 37 of period 1, Wednesday, May 27th. Today we're reviewing some of the content in chapter 2. Today's the first lesson is about the types of radiation that is mentioned in the textbook. There are other types, but these are the three most important ones. There are alpha, beta, and gamma radiation. I showed you the symbol of each one. They're Greek letters, alpha, beta, gamma. Alpha radiation is basically a helium nucleus being hurled out of a atomic nucleus. So it carries away the energy of whatever interaction has taken place, usually the breaking up of a nucleus through fission, or perhaps if some other type of radiation hits the nucleus, it can cause the atom to fragment. And sometimes what's emitted is an alpha particle. The charge on an alpha particle is +2, and it has about 5% the speed of light. So they're moving very quickly. They can go even faster than that if they come from more energetic collisions or radioactive decays. And you can even get alpha particles that are the result of cosmic rays. Cosmic rays happen when stars go supernova, and the amount of energy released during a supernova can actually briefly exceed the entire output of the galaxy. So it's an immense amount of energy being released, and then you'll get alpha particles that are approaching the speed of light, and they'll go zipping through the universe until they run into something. Beta particles are just electrons moving really fast that have been ejected from a nucleus. Their charge is -1, and their velocity can probably go higher than the speed of alpha particles because they're much lighter particles. Electrons are much lighter. So I couldn't find the reference that said with any specificity what velocities to expect, but I'm guessing it's variable, and it's higher than 5% of the speed of light. And finally, gamma rays are simply light. It's a form of highly energetic light. Just like we look at visible photons that fall in the range of 400 to 700 nanometers wavelength, the wavelength of gamma rays is even shorter than X-rays. So gamma rays are highly penetrating radiation. They can go through several feet of concrete, and they can even penetrate into lead. So it's a dangerous form of light. It's not like you can be exposed to gamma rays, and if you could even see gamma rays, it still wouldn't be a good thing to go look at them, because they would damage all living things. In fact, gamma rays can even damage regular atoms. They actually break down atoms when the intensity is right. So those are the three principal types of radiation. You should be familiar with what they're made of. So alpha radiation is a helium nucleus, beta radiation is a high-speed electron, and gamma rays is just high intensity, very short wavelength of light. The next thing I want to review with you is number 216, question number 216 in chapter 2. So let's have a look at that. The question is, an atom of tin, as said, has a diameter of about 2.8 times 10 to the minus 8 centimeters. A, what is the radius of a tin atom in angstroms and in meters? And B, how many tin atoms would have to be placed side by side to span a distance of 6 micrometers? C, if the atom is assumed to be a sphere, what is the volume in meters cubed of a single tin atom? So we'll start off with 2.8 times 10 to the negative 8 centimeters. And we're going to convert that to meters by using the conversion factor between centimeters and meters. It's 100 to 1. There is 1 meter for every 100 centimeters. You notice I put 100 centimeters in the denominator so that I can cancel centimeters. And there are 10 to the power of 10 angstroms per 1 meter. So it's not an SI unit. It's basically 10 times smaller than a nanometer. So 1 nanometer equals 10 angstroms, and that symbol is, I guess it originated in Germany. And that allows you to cancel meters. So you have 10 to the negative 8, 10 to the 2, and 10 to the 10. If you bring the 10 to the 2 upstairs, it becomes 10 to the negative 2. So you have negative 8, negative 2, which adds up to negative 10, negative 10, positive 10. That's going to give you 10 to the 0. So what you have is 2.8 angstroms times 10 to the 0, which is 1. So you still get 2.8 angstroms. And what's the question actually asking? It's asking, what is the radius? Well, we just calculated the diameter, so the radius is 1/2 of that. So radius equals 1.4 angstroms for a tin atom. And if you are going to convert it to meters, you can just do the calculation like this: 2.8 times 10 to the negative 8 centimeters times 1 meter per 100 centimeters times, that's it, you're done. That equals 2.8 times 10 to the negative 10 meters. And then that's the diameter, so the radius would be 1.4 times 10 to the negative 10 meters. That would be the answer for the second part of A. In part B, I think we might be able to squeeze it in here, so we'll do that here. Part B, just to reiterate, it says how many tin atoms would have to be placed side by side to span a distance of 6.0 micrometers. So 6.0 micrometers times 1 meter per 10 to the 6 micrometers equals 6.0 times 10 to the negative 6 meters. I'm just putting that upstairs, so 6 times 10 to the minus 6. And because each atom has a diameter of 2.8 times 10 to the negative 10 meters, it's going to require 21,428.57143 atoms. Of course, we're not going to report that. We're going to report 2 sig figs. So we're going to say 2.1 times 10 to the 4. How did I get 10 to the 4? I said 1, 2, 3, 4 jumps to get the decimal place to here. So that, because I moved it that way, or the better way to look at it, I made this number 10,000 times smaller. So I got to multiply by something 10,000 times bigger. So from 10 to the 0, I go to 10 to the 4. And that's how many atoms we have, written in scientific notation. The last bit asks, if the atom is assumed to be a sphere, what is the volume in meters cubed of a single tin atom? So the radius is equal to 1.4 times 10 to the negative 8 centimeters times 1 meter per 100 centimeters. So we're back to, well, I should have just, okay. 1.4 times 10 to the negative 10 meters is the radius. Volume of a sphere is 4 over 3 pi r cubed. We're going to enter in the value of r in meters, 1.4 times 10 to the negative 10 meters. You can raise that to the power of 3. What you get is 4 over 3 pi times 2.744 times 10 to the power of negative 30. So when you multiply all that through, you get .149404.032 times 10 to the negative 29 meters cubed, and that gives you 1.1 times 10 to the negative 29 meters cubed. Next is 223 from the same chapter. It's how to calculate all the different proportions of protons and neutrons within an atom, which you should be able to do with ease. It's an easy question. So I'll copy the chart for you and then reason you through it. So the chart has the following headings: the symbol, the protons, neutrons, electrons, mass number. Okay? And then they give you one clue for each one. So on the first one, they give you the symbol, which is chromium with a 52. Second one, they give you the number of protons the thing has, 25. The third example, they give you the number of neutrons and the number also give you the clue for the next atom. And they give you the one below it. And then they give you the one next to it. And last, they give you 207. Okay, there we go. Oh, and they give you the number of protons in that as well. Cleans up our table. So how do we find what each one has? In the first case, we have chromium with a 52 as its mass number. Remember, the mass number represents the number of protons plus neutrons, right? So if you look at any periodic table, you'll see that chromium has 24 protons, so that the number here is 24. So it's got 24 protons, which means it has to have 28 neutrons, because 24 plus 28 adds up to 52. The number of electrons is going to be the same as the number of protons, so in this case it's going to be 24, because the chromium doesn't have any charge. And finally the mass number is 52, and that's written over here. This atom has 25 protons, and if you have 25 protons, your name is manganese, and your mass number is 55, because 25 plus 30 gives you the 55. The number of protons, there's no charge in the manganese, so that means you have the same number of electrons, 25, and the mass number is already there, so we're going to put 55. This element has 48 electrons, and we're going to assume it has no charge because no other indication is given, so that's cadmium. If you look it up on the periodic table, element number 48 has 48 protons, that's what we can write in here. And if you add 48 plus 64, you get 112, and cadmium's mass number is 112, and we can also write that in over here. Something that has 86 electrons, if it has no charge, its name is radon, and therefore it has 86 protons. You can write that in over here. The mass number of radon is 222, which means you have to have 136 neutrons. 136 plus 86 gives you the 222. The last one, mass number 207, is lead. Lead has a mass number of 207, and it has 82 protons. which means it must have 125 neutrons, because these two numbers added together gives you that number. And if it has no charge, and in this case they don't indicate that there's any charge, then it'll have the same number of electrons as it has protons, so that's 82. That's our chart filled in. Next thing is isotopes. Isotopes are atoms that exist but with variations in the number of neutrons. So we can use carbon as an example. Now the name of an atom is given by the number of protons. So if an atom has 6 protons, it's a carbon atom. But there are varieties of carbon atoms. There are carbon atoms with 6, 7, and even 8 neutrons. So they all have 6 protons, but this one's got 6 neutrons, this one's got 7 neutrons, and this one's got 8 neutrons. So this whole series of elements is called isotopes of carbon. And many elements have isotopes where there's a principal isotope, the one that occurs most often, usually not radioactive because it's the most stable one, and then there's other ones where it is radioactive and it's got variations on the number of protons. For example, uranium. Uranium-238 is not radioactive, or it has a very low radioactivity, very long half-life, whereas uranium-235, which has 3 fewer neutrons, same number of protons, 92 protons, but 3 less neutrons, uranium-235 is radioactive. And that's the kind of uranium they use for making bombs, and they also use uranium enriched in uranium-235 to use in reactors. They enriched so much uranium-235 during the Second World War that all the leftover uranium-238 was in huge stockpiles, which they then decided to use as bullets, because uranium has a very high density. And the other peculiar property of uranium bullets is that when you fire them, they get sharper as they're entering into a piece of metal. So they ablate. The outside edges of the bullet actually wear off, and the bullet gets pointier as it's going through the target. So it has great penetrating properties for shooting at armor. You know, if you're shooting at a tank with armor that's a foot thick, it takes a lot of energy to get through the armor. So that's one of the types of bullets they use. But the bullets are mildly radioactive. So some people believe that Gulf War syndrome is attributable to the fact that they used radioactive ammo for shooting at the tanks and the armored vehicles. Anyway, let's do an example where we do a calculation to find the average molar mass of an element that happens to have several isotopes. That is question number 230, sorry. So in 230, the question is, the element lead consists of 4 naturally occurring isotopes with atomic masses 203.97, 205.97, 206.97, and 207.97. I omitted some decimals for brevity. The relative abundances of these 4 isotopes are 1.4, 24.1, 22.1, and 52.4%, respectively. From these data, calculate the atomic weights of lead. Okay, so I'll show you how I did that calculation. What you do is you take a mass, a weighted average. And how do you do a weighted average? You take the mass that's reported, so I write that first, 203, and it doesn't matter if you write it first or last, but I'm just, for the sake of neatness. So there's the mass of the first isotope, and has an abundance of 1.4%. Right. So how do you write 1.4% as a decimal? You say 0.014. That's the first proportion. Then the next isotope has a mass of 205.97444. and that has a 24.1% abundance. That's how you write that. And then you add 206.97587, and its abundance is 22.1%. So you're going to say times 0.221. And lastly, you have the one that weighs 207.216884 grams per mole, and it's, no, I'm copying the wrong one, 207.97663, and it has a 52.4% abundance. You write that as 0.5240. So you convert the percentages into decimals, and the result is when you plug it all into your calculator, you get 207.216884 grams per mole is the average molar mass of lead based on that isotopic abundance. If you look at the periodic table, you'll see that they put the molar mass of lead to only one decimal place. And the reason for that is that depending on the source of the lead, depending on what material it has decayed from, you get different abundances, different percentages of the isotope abundances. So lead has different average masses depending on where you find it, which mineral you find it with. So it makes no sense to have it to multiple decimal places unless you're getting it all from the same place and the same mineral. Anyhow, it's reported to be 207.2. If you use the proper sig figs as well, because we only went to 2 sig figs here, 3 there, 3 there. I'm going to 4 sig figs already. The way it was reported in the book, though, the percentages were reported to 3 sig figs. So really, I shouldn't. You could maybe argue this is 3 sig figs depending on how they measured it. I really shouldn't be going past 207. The next question I would like to do with you, let's review, is some nomenclature. 2 questions, 259 and 265. 259 and 265. One is for ionic compounds, and the other one is for molecular compounds and how to name them. And you can watch my nomenclature playlist as well, doing yourself a favor. I'm not going to test you on that, because how are you going to test something like that on the internet? But I will urge you to learn it, because in university it's a useful thing to know what chemicals are called. Alright, let's look at 259 first. So 259 is all ionic compounds. Now, ionic compounds are made up of a metal with a non-metal. So one is on the left side of the periodic table. You know that metals are all on the left side of the periodic table because you studied the periodic table. And non-metals are on the right side of the periodic table. So whenever you have a metal with a non-metal, it's an ionic compound because one has a positive charge. The metal always has a positive charge. And the non-metal, or the polyatomic ion, usually has a negative charge. So let's name the different things. Start off by drawing them. Actually, we're going to need more room than what we have now. So I'm going to erase all that. Let's do a little time check, because I know the internet cuts me off at around half an hour. Or my phone, I don't know. Maybe it's my phone overheating. I did say 259. Of course, I did it all backwards, okay. I'll do it the same way I did it in my notes. So MgO is magnesium oxide. Question B, they have AlCl3, that's called aluminum chloride. If you're from the UK, they add an extra I right after the N, so they say aluminium chloride. But aluminium, whatever you like. Both of them are correct. Li3PO4, lithium phosphate. D is barium chlorate. No, that's a perchlorate. Barium perchlorate. So if you know your polyatomic ions, it opens up a million possibilities. So you should memorize those. I did urge you to do that at the beginning of the year. E has a copper with 2 nitrates. Nitrate is -1, and copper, when it has the higher charge, is called cupric, so you call this cupric nitrate. F has FeOH2. That's the lower form of iron, because it's Fe2 and Fe3, so one is ferrous, the other one is ferric. The higher one is always ic, so this is ferrous hydroxide. G has calcium with, it looks like acetate, yeah, C2H3O2, taken twice because calcium has a +2 charge, acetate has a -1 charge, so you call this calcium acetate. Incidentally, acetates are all soluble, almost all of them are soluble, and same with nitrates. If you want something soluble, acetate or a nitrate is usually soluble in water. H is Cr2 with CO3 taken 3 times. So it's chromic carbonate. Carbonate has a -2 charge, chromic has a +3 charge. They have to equal out, so 2 chromics gives you +6, and 3 carbonates gives you -6, and that's going to balance out. And when you make your ionic compound, obviously it has to balance out. So K2CrO4, that's called potassium chromate. And the last one, NH4, taken twice with an SO4, is ammonium sulfate. Voila. Now the last one is for, so that was all ionic compounds. The last one I want to do with you as a review is 65, which is all binary compounds, or molecular compounds. And those ones, you just use prefixes to name them. Like mono, di, tri, I showed you them in the notes. And you can also watch my playlist on nomenclature. I have all kinds of explanation on there. Just brush up a little bit and then you'll thank yourself. 265, it goes up to F, A, B, C, D, E, F. So you have SF6, IF5, ZeO3. Then the other one, they start giving you the name and they want you to draw the thing. Tetraphosphorus hexasulfide. So let's name these. This is sulfur with 6 fluorines is hexafluoride. So they always end in "ide." Always end in "ide." You can also say monosulfur, but you can drop the mono. This would be iodine penta for 5, fluoride, fluoride. Xenon trioxide. You could also say, if you want, monoxenon trioxide, but if you leave out the mono, it's assumed there's only one. Dinitrogen tetroxide, N2O4. Hydrogen cyanide is HCN. And tetraphosphorus hexasulfide is P4S6. And that's enough for today. For your homework, I would recommend that you watch my Polyatomic Ions playlist. It's in my nomenclature playlist. Watch the Polyatomic Ions video once. Just watch it once, about 2 minutes out of your time. That's your homework, okay? See you tomorrow.